We don't know. But anyway, Theodorsen was not concerned or interested in the step input. He wanted to solve the flutter problem of airplane, for which we have continuous oscillation. So simple harmonic motion. This was in the back of his head. So we're gonna proceed for that, but it's the exact same integral equation. Anybody working in unsteady aerodynamics will, at the end, arrive at this equation. Okay? Integral equation for separation. Any question, please?
Sir, for the alpha 3/4, but if we put an extra term there for the step response, the step response equation in terms of time, the one with the exponential, to kind of.
Yes, so this is exponential. The solution will be exponential.
Okay.
So the solution for this equation would be, 1 minus e to the negative something t. Yes. So let's see how Theodorsen proceeded. And like I said, Wagner function is not known as explicit function of time. But Theodorsen managed to get an explicit function of time for the frequency response. Let's see how he did. Was very lucky and also very sharp mathematically. So, do you remember how we get the lift? Usually, how we get lift in general?
Yo-yo gamma?
Yes, but within this framework, when we started, how we get lift in the non-circulatory? You remember this? We got v theta, then phi, then lift, right? The exact same thing we'll do. It's the same relations, but v theta now is different. Okay, we got a different v theta. So let's do that. So we have v theta distribution. Here is the v theta distribution for any theta. This one, right? Okay. So actually, the velocity potential, the circulatory one at any theta, is negative b over 2. The integral from theta to pi is the same relation, right? Governing v theta and phi. Okay? So this is negative b over 2, integral from theta to pi. Let's copy v theta circulatory, please. This is negative gamma over pi b, so negative gamma over pi b. It doesn't matter if you put a single vortex or a distribution for them, because we're integrating over theta. Okay? At the end, we're going to replace gamma by a distribution. So let's get it for a single vortex and then replace it by distribution. We're integrating over theta. It has nothing to do with the location of gamma, which is z. Gamma over pi b, x squared minus b squared over 4 divided by x squared plus b squared over 4 minus bx cosine. I need it as a function of phi because I will integrate with respect to phi. Okay? So what do we have here? We have this guy. So this is gamma over pi b. And this is outside, integral from theta to pi d phi over this term. I'll call it a. It's a constant with respect to phi because I'm integrating with respect to phi. So this is it's not a very difficult integral. Whatever it's difficult or not, I will give it to mathematical and it will give me its thing, right? I'm integrating with respect to phi, and so here is the thing actually. It's actually one of this thing. And it's tan inverse. It's 1 over x squared minus b squared over 4. Tan inverse x plus over x minus tan theta over 2. Between limits. So you can see that these guys go away. And we have our velocity potential at any theta is equal to gamma over pi b, right? Tan inverse Again, x plus b over 2x minus b over 2, I'll replace it with the z's. Tan theta over 2 between theta and pi. So it's gamma over pi b. If you substitute theta for pi, tan pi over 2 is almost infinite, so it doesn't matter this value. And you have the tan inverse of that, you will get what? Tan pi over 2, it's a very large number, it doesn't matter this coefficient. So it goes to infinity, and tan inverse of that is pi over 2 again. Minus, you substitute theta for theta. I'm sorry, this should be 5. Because we're integrating over 5. It doesn't matter. So tan inverse z plus b, z minus b. This is, I mean, I can drive it for you here, but it will take maybe 1 minute. But I'd like to save it because it's not my thing here. I guess this is 1 minus cosine phi, 1 plus cosine phi. If you don't believe it, I can do it for you. So 1 minus cosine theta, 1 plus cosine theta. This is the velocity potential. We're done with it. So next step is get left. Here just simply tan is sine over cosine. Multiply both up and down by cosine, phi over 2, to get sine up, which is the square root 1 minus cosine squared. And you know, you play a little bit, you will get this. If you have any question, please stop me. At the end of the day, we'll have a nice expression to apply if I want to get the left as a function of time. But I really cautious that you guys know how these steps evolve, because I want you to know how to develop your own model if you want. So if you remember, okay, from v theta we get phi, we just need 2 things of phi to get the left. If you remember the formula. It's just 2 things. We need phi at the trailing edge, which is phi at theta equals 0. So let's substitute at theta equals 0 here. So this gives you 0. So the right term, the second term is all 0, and you get gamma over what?
2b.
Yeah, I guess there is. Oh, the b goes away. I don't know why I get. There's no b. Okay. So you get gamma over 2. And then the second term in the left expression, you remember what was that? We usually need phi at the trailing edge and the unsteady term. Do you remember it? The unsteady Bernoulli equation? It's partial phi, partial t. So look at this expression, and we need to differentiate it with respect to time. Okay, we need to differentiate this with respect to time. Which variable is varying with time? So we have gamma, z, theta, right? Of course, b is not varying with time. This is the whole thing. So which of these 3 things are varying with time? This is your plate. This is b. This is your vortex in the wake. Later on, at the end of the day, we replace this by distribution, but it's very reasonable to deal with one at a time. This is at a location z. Okay? So theta is the coordinate on the cylinder. This is independent variable. That has nothing to do with time. Now we have gamma and z. Which is time varying? When we have, so either the plate is moving, so in the plate coordinates, this guy is going backward, or the plate is fixed, then we have u infinity, the same thing, this guy is time varying. Okay? So this tells you that what variable is time varying? Z, very good. And Z dot will be what? Will be the local speed of the vortex. When we do it numerically, we're really gonna compute the local speed of the vortex and convect it by this thing. But here we are in an analytic fashion, so we need a good approximation. So the plate is moving up and down, small disturbance, and the mean flow is u infinity, so it's very fair to assume that the speed here is u infinity to the right. So this guy is u. Okay? Z dot is u. What about gamma? This gamma time varying. It's gamma time varying.